This lecture we're going to talk about power series. If you're following Stuart's book, we will be skipping sections 11.8 and 11.9, but we'll introduce the material we need from there as we go along. So firstly, I want to recall a few things. First thing, a series, sum n equals 1 to infinity a n, is defined to be limit k goes to infinity of sk, where sk is the kth partial sum. That's you add up the first k things. So this is the limit k goes to infinity of add up the first k things. You add up one thing, then you add up the first two things, then you add up the first three things, and you add up more and more and more and more. And this limit is this, I put it in quotes, idea of adding up all of the terms, adding up infinitely many terms. Okay, second thing, a geometric series. This is a special type of series. Is a series of the form sum n equals 0 to infinity a r to the n. And that is a plus ar plus ar squared and so on. A is called the first term for obvious reasons. And R is called the multiplier or common ratio. Okay, so the special thing about a geometric series is you start off with a number a, and to get to the next term you just multiply by r, and you keep multiplying by r and putting plus signs down. Okay, that's a geometric series. Now we showed before, for r, absolute value of r less than 1, this series converges. And in particular, it converges to a over 1 minus r. We also showed for absolute value of r greater than or equal to 0, this series, a r to the n, does not exist, i.e. the limit does not exist. If you keep adding up more and more terms, this limit does not exist. You can say the series does not converge, etc. Okay, so let's start a new page. Okay, so I want to make a quick remark before I move on to the next point. For each r, let's just think of a as being 1, this geometric series is a different series. You can think about r as being a half, r as being a third, r as being 7. Each different r gives you a different series. Now we know that for each r with absolute value of r less than 1, this series is a number. So for each of these r's, this series is a different number. Now, why am I mentioning this? So, we could think about inputting r, again with absolute value of r less than 1, and outputting this number, this series, sum r to the n. And in particular, this equals 1 over 1 minus r when we have this condition on the size of r. So what does this remind us of? Inputting a number and outputting another number. This brings me to my third point. A function is, in a hand-wavy kind of way, a machine. We think about plugging in an x into the machine, let's call it f. We usually call the input x, the machine f, and the output is f of x. So what is this to do with geometric series? Well, we can think about plugging r into the geometric series machine, g, and getting out r to the n, this geometric series. Now, this machine only makes sense if the inputs have absolute value less than 1, because otherwise the output is going to be nonsense. It's going to be some sort of series that doesn't even converge. So we have taken an idea of a series and developed an idea of a function from it. And this is going to be the entire point of the discussion in this lecture. We are going to establish some sort of connection between functions and these special types of series. And that's going to be the goal of the lecture. Okay, so let's start with the first definition of the lecture. Definition. A power series centered at 0, and this will become relevant later, is a series of the form sum n goes from 0 to infinity Cn x to the n, where x is a variable and the Cn's are constants called the coefficients of the series. Okay, so going back to this idea of a function, we think about taking x, inputting it into this power series machine, and what we get out is this series, Cn x to the n, goes from 0 to infinity. If we were to write this out in the dot 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 notation, that would be C0 plus C1 times x, plus C2 times x squared, plus C3 times x cubed, and so on, and so on, and so on. Okay, let's look at some examples. Firstly, sum x to the n equals 0 to infinity. So here the Cn is just 1, because if we were to write this out, it would be 1 plus x squared plus x cubed, so the Cn's are all just 1. Second example, x to the n over 2 to the n. It goes from 0 to infinity. And we can see again here that Cn is 1 over 2 to the n. Okay, so remark the Cn's are really what determines the power series. So different Cn gives you different series. You always have this x to the n, but it's the Cn that controls which series it is. So different Cn's give different series. Now, fundamental question. If we want to think of this as a function, if we want to think of it as a machine, what is the fundamental question for any machine? Well, that is, what can you put into it? For what values of x does the series sum n goes from 0 to infinity Cn x to the n make sense? What x's can you plug into this machine? I.e., for what values of x does this series converge? And that's going to be the fundamental question when talking about power series. If I'm to define one of these power series, if I'm to tell you what the Cn's are, you need to ask, well, what values of x does it make sense to plug into this machine? Okay? Now, we'll develop more sophisticated tools for answering this question in the next lecture, but we're going to see some examples of figuring out what values of x make sense to plug into different types of power series in this lecture as well. Now, the first example we're going to consider should look a bit familiar. G of x is defined to be 1 over 1 minus x. Now, using the domain convention, the only x that doesn't make sense to plug into G is 1, because then you're dividing by 0, so the domain is everything except 1. Now, for absolute value of x less than 1, g of x is, well, it's just 1 over 1 minus x, but using the formula for a geometric series, here I have an x instead of an r, but it doesn't matter what letter I use. This is the sum x to the n. 1 plus x squared plus x cubed, etc. Okay, so what have I done? I have represented G as a power series on a certain domain. Represented our function G by a power series but only on a smaller domain. Because remember, this formula, this equality, that 1 over 1 minus x equals this series, only makes sense for absolute value of x less than 1. So I have G that goes from minus 1 to 1 open. This is absolute value of x less than 1 into R, where G of x is 1 over 1 minus x. And that is the same for these x as this series. I.e., this power series representation for G is only valid on minus 1 to 1. So, why would I ever want to do this? I have lost part of the domain of G. I've represented it as a power series, but the formula is only valid on this smaller domain. I originally had G everywhere except 1. So why would I want to do this? That's a very reasonable question. I think it should be the first question you should ask. So why would I want to represent G in this way? Well, first reason. Power series are easy to differentiate and integrate. And we'll see this later, exactly how you differentiate and integrate a power series, but they're easy to differentiate and integrate. So you could have some very complicated G that's hard to integrate, hard to differentiate, and we could represent it as a power series, and these are easy to differentiate or integrate. Second reason, power series are very useful for numerical estimations or approximations. This is what your computer is going to do. It's going to take a function and represent it as a power series. Like in your calculator, sine and cosine are represented by power series. And what your calculator does is it plugs into the first few terms of the power series. We'll talk about that more later. But these are the two main reasons for why you would want to represent a function by a power series. So we've established a connection between the function 1 over 1 minus x and this power series, this geometric series. So the next question should be, can we represent other functions as power series? Can we represent other functions as power series? Now we saw that for the G we had in the last example, it was only valid for absolute value of x less than 1. So the next question should be, if we represent another function as a power series, where will these representations be valid? So for what values of x will these representations of the functions as power series even make sense? Okay. One method of answering this question is the method of substitution. So pretty much we're going to use the formula that we got from expanding G as a power series, and we're going to use that to give us other expansions, other representations of different functions. So the best way to see this is just in an example. So we're going to look at a couple of examples. Find power series representations for the following functions. Identify where the representations are valid. And give a formula for the CNs, because remember each power series is defined uniquely by the CNs. So, first example, hx is 1 over 1 plus x. Second example, jx is 1 over 1 plus x to the 7. Okay, so at this point of the video, pause the video, attempt these examples, and then afterwards I'll start the solution. You can check your answer against that. Okay, so let's look at the solutions to those examples. Now I mentioned we'd be using the method of substitution, so let's recall what we have. We have, for absolute value of x less than 1, that this series, x to the n, is equal to 1 over 1 minus x. Now, we didn't have to use x. X is just some letter that we decided to use. We could have easily used, let's say, w. And we would add 1 over 1 minus w equals the sum of w to the n. W could be as mad as you want. This formula is still valid as long as it's of size less than 1. So let's solve the first problem. h of x is equal to 1 over 1 plus x. I can rewrite this as 1 over 1 minus x. Now, this is the sum, minus x to the n. N goes from 0 to infinity. When is this formula valid? Well, the thing I want to plug in is minus x, so I need that minus x has size less than 1. Otherwise, this equality makes no sense at all. This is equal to, take out the minus 1, write minus x as minus 1 times x, and we get this. And clearly here, our CNs are minus 1 to the n. Now, minus x, absolute value of it less than 1, is the same as absolute value of x less than 1, because absolute value doesn't care about sign. Okay, move on to the second example. J of x is equal to 1 plus x to the 7 under 1. Is equal to, again, the same trick. We write x to the 7 as minus x to the 7. And this is sum is 0 to infinity minus x to the 7 to the n, which is, separate them out again, minus 1 to the n, x to the 7n. It goes from 0 to infinity. Now this is 1 minus x to the 7 plus x to the 14. This is not the same as the other power series we looked at. It's not x to the n, it's x to the 7n, so we have to be a little bit more careful. Now, C0 is 1. C1, well, there is no x term, so C1 is 0. C2 is 0. There is no square term. All the way up until we get to C7, and we saw that it's minus 1. C8 was 0, there's no x to the 8th term. And so on up to C14 is 1. C15 is 0, and it goes on like this. So it's a much more complicated collection of CNs than the first example. Now, when is this equality valid? I can't always write this. This is valid for, well, what's the thing I'm plugging in? Minus x to the 7. Its absolute value less than 1. That's the same as absolute value of x to the 7 less than 1, which of course is the same as absolute value of x less than 1. So We found a power series representation for h and for j, and we found where they're valid. And we've identified the CNs. Next thing I want to do is look at a remark. For x such that this power series converges, so for an x value such that this series makes sense, what can we say? First remark, if I take a constant k and multiply it by this power series, then I can do the thing that I would want to do if I was only adding finitely many terms. I just multiply k by each piece. So as a sentence, this is we can bring constants inside power series, as long as it's an x such that this power series converges. Second, I can multiply the power series by some power of x. And in exactly the same way, I can bring that inside. And I get x to the n times x to the m. And what do? I add the exponents. Okay, so this is going to be very useful for doing more examples. So let's see some cases. First example. F of x is 2x over 1 plus x. Second example, h of x is 3x to the 4 over 1 plus 5x squared. Last example, g of x is 2x over 4 plus 3x cubed. Okay, so I want you to approach this the same as the last bunch of examples. Find power series representations and decide where these representations are valid. Okay, so let's run through the solutions. First example, f of x was 2x over 1 plus x. So we take out the 2x, we've got times 1 over 1 plus x, which is equal to, from the last example, 2x times this series, which, using the remark, we then bring in the 2 and we bring in the x. We have 2 out in front, and then the x times x to the n is x to the n plus 1. And again, this equality here is only valid for absolute value of x less than 1. So we've successfully expanded f, and we know where this expansion is valid. Second example, h of x was 3x to the 4 over 1 plus x to the 5. Again, we're going to take out the 3x to the 4. We're going to have that times 1 over 1 plus 5x squared. This is equal to 3x to the 4. Following the same vein, we're going to write the second part as 1 minus 5x squared under 1. Now this is equal to, where is this valid? Now I'm going to use the same trick, but to use this trick I need that minus 5x squared is less than 1 in absolute value. That's the same as saying, if I drop the minus sign, then I can take out the 5 and bring it under, so I have absolute value of x squared is less than 1/5, which is the same as the absolute value of x is less than 1 over the square root of 5. So that's where this is valid. So 3x to the 4 minus 5x squared in a geometric series equals x to the 4, sum, and equals 0 to infinity, separate out the minus 5, and x to the 2n to the n is just x to the 2n. Now bring in the 3 and the x to the 4. We get 3 times minus 5 to the n, x to the 2n plus 4. So here, the interesting thing about the second example is it's the first example where we've seen where the interval of x, where the formula makes sense, isn't just absolute value of x less than 1. We have absolute value of x less than 1 over square root 5. So this interval where the series makes sense, i.e. where it converges, can change in size. We've seen that. Okay, so let's move on to the third example. G of x equals 2x over 4 plus 3x cubed. Now let's take out 2x over 4 because we want to use the trick where we have 1 over 1 minus something. So to make that 4 at the bottom of 1, I'm going to take 4 out of every term on the bottom. So I'm left with this. This is equal to, if I have 2x over 4, that's going to cancel one of the 2's, and I just get x over 2 times, same trick, 1 minus 3 over 4x cubed under 1. Okay, now this is a little more complicated. Remember, I want to use the same trick, the 1 over 1 minus x trick. So where is it valid? Well, it's valid for the thing. The thing in our case is minus 3 over 4x cubed less than 1 in absolute value. We do some algebra on that. We're going to get overall absolute value of x less than the cubed root of 4 over 3, which is the most interesting interval we've seen so far. And now I can use this equality. So it doesn't matter, again, we had the case where we had 1 over 1 minus w. It can be whatever you want as long as the size of that thing is less than 1, which was the algebra we've done in the turquoise. Working through more of the algebra and bringing the x over 2 inside using the remark, we have sum n equals 0 to infinity minus 1 to the n, 3 over 4 to the n, a half times x to the 3n plus 1. And there we have it. We have the interval where it makes sense, and we have the formula. Okay, so exercise. This is something you should try yourself. Find a power series representation or expansion of the function below and determine where the expansion is valid. G of x is 2x squared over 3 minus x. Okay, so try this as an exercise. If you want to check your answer, this is worked out on page 11 of the printed notes. Okay, so the next thing we want to consider is the center of a power series. Okay, so let's look at the following example. Consider the function f of x equals 1 over 4 minus x. Say we want a power series representation of f of x. Let's see now that we can actually approach this multiple ways. So here's method 1. This is going to be generally in line with what we've been doing so far. So we're at f of x as 1 over 4 minus x. Now we usually want 1 over 1 minus something, so we take out the 4, and we've got 1 over 1 minus x over 4. So we write that as 1 over 4 times the sum from n equals 0 to infinity of x over 4 to the n. And remember, this is only valid as long as x over 4 in absolute value is less than 1. So this, just bringing the quarter in, is going to be sum n equals 0 to infinity 1 over 4 times 1 over 4 to the n times x to the n. And that's equal to, if we multiply the 1 over 4 times the 1 over 4 to the n, we get 1 over 4 to the n plus 1 x to the n. Okay, and just to elaborate more on where this is valid for, x over 4 less than 1 implies that absolute value of x is less than 4, i.e. x can be between minus 4 and 4. Okay, now let's see method 2. Method 2. F of x again is just 1 over 4 minus x. But this time we're going to write it as 1 minus x minus 3 over 1. Now, that's equal to, using exactly the same philosophy as if I had a w, I can plug in whatever I want, is equal to this geometric sum, as long as the absolute value of now x minus 3 has to be less than 1. So this is equal to 1 plus, in the dot 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 notation, x minus 3 plus x minus 3 squared plus dot dot dot. Okay, now let's flesh out where this is valid for. What this means is that the gap between x and 3 has to be less than 1. So if we're at 3, we can only go 1 to the right, which would be 4, and 1 to the left, which would be 2. So that means that x has to be between 2 and 4. Okay. Here we had from minus 4 to 4. Here we have from 2 to 4. So we found two different power series expansions of the same function, but they're valid for different intervals. So remark, the interval, and what do we notice about the difference? What's different about this second type of interval? The interval in method 2 is centered at 3 rather than centered at 0 like all the intervals we've done before this have been. Okay? And this is going to motivate the next definition. Okay, so definition. A power series centered at A is a power series of the form sum Cn x minus A to the n, from n is 0 to infinity. Now expanding this out in the dot 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 notation, this would be C0 plus C1 x minus A plus C2 x minus A squared plus C3 x minus A cubed, so on. Okay, where, just to introduce some terminology, A is a constant, x is a variable, Cn's, again, are constants called the coefficients of the power series. And A is often referred to as the center. So A is a constant called the center of the power series. Okay, so this is why our previous definition was a power series centered at 0, because we only had x, and that's the same as x minus 0. So this is a power series centered at A. Okay, so remark. One. If we think about this as a function, which we've done before, in exactly the same way, if we plug in a for x, what do we get? We get Cn a minus a to the n. Now, if we write that out in the dot 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 notation, that's C naught plus C1 a minus a plus C2 a minus a squared. What do we notice about all these a minus a's? Well, they're all 0. So the only term that survives is going to be C naught. So what have we inferred from this? We can think about the power series centered today as a machine. Now this is very important, NB. A power series centered at A always converges for x equals A. So no matter what the CNs are, you can always plug in A, and this function always makes sense at A. So in particular, power series centered at 0 always converges for x equal to 0. So in any of the power series we've seen before, plug in x equals 0 makes sense when we've expanded it as a power series centered at 0. So anything except method 2 in the last example. So if we are interested in the behavior of a function f near A, okay, so for values of x that are close to A, it can be useful, if possible, because it's not always possible to represent it in an interval, to expand f in a power series centered at A on some interval. Now when I should say you can always expand it on the interval just A, like the 0 width interval, but if you can expand it on a non-zero width interval, then it can be useful, because if you look at the terms, you have your C0 plus, and then you're going to have C1 x minus A. So when x is close to A, those x minus a's are very small. So you can approximate the behavior of your function by taking the first few terms, and we'll see that later on. That's the philosophy. Okay, so let's look at an example. Sum n equals 0 to infinity of x minus 1 to the n over 3 to the n plus 1 cubed. And this is an example of a power series centered at 1. So you don't care how mad the CNs are, you're looking at the x minus a to the n piece. So this is a power series centered at 1 because a is 1 in our example. Okay, so remark, again, a power series defines a function f of x equals sum n equals 0 to infinity Cn x minus a to the n. So you give me an x and I can plug it in, replace it in that series formula. Fundamental question again. What x can I plug in here? What x makes sense to plug into this series? So if I'm going to tell you this thing is a function, you have to ask me what is the domain of this function. I.e., for what values of x does this series make sense or converge? So we're going to look at a theorem now that's going to answer this question. Okay, so theorem. For any power series, sum Cn x minus a to the n, there are only three possibilities for describing the values of x for which the series converges. Possibility 1. The series converges only for x equal to a. So we know the series always converges at x equals a. The first option is that that's the only place where it converges. Second option, so that's the first case is the worst case scenario. Here's the best case scenario. The series converges for all x in R. So for every number, every real number you can think of, it converges. Makes sense. You can plug any x element of R into your power series. Third option, there is a positive R such that for absolute value of x minus a less than r, as in for an x that's r away from a, less than r away from a, the series converges. For absolute value of x minus a greater than r, the series diverges. And inconclusive on the boundary. So inconclusive when a is exactly r away from x. Okay, so in pictures, what does this mean? Well, the first case means if we draw the number line and we mark a, then we highlight in yellow where we converge. It's literally just at the point a. In the second example, we can highlight a again, and where do we converge? Well, we converge on all of R, so we highlight the entire real line. Now the third case is the interesting case. We mark down A, and then we have to look R to the right and R to the left. Those two don't look the same, but just imagine they're the same length. Then we know that we converge inside this bracket. And we don't know what's happening at the edge case. So when you're exactly R away from A, we're not sure. You have to check those cases individually. But if you're outside there, this orange means that we diverge. Okay, so I'll fill in those two boundary points. The blue dots we don't know, but for the yellow inside this open interval, we know we converge. If we're outside this interval, we know we diverge. And on the boundary cases, again, we have to check them individually. So this summarizes the three possibilities for describing the values of x for which the series converges. So your power series either converges just at A, converges on every point on the real line, or it converges on some interval. Intervals centered at A, with potentially the endpoints or not. So it could be open interval, it could be half open interval, or it could be closed interval. But it's always centered at A. So this theorem leads us to the following definitions. First definition: if such an r greater than 0 exists, as in case 3 in the previous theorem, for a power series sum n from 0 to infinity, Cn x minus a to the n. Then we say r is the radius of convergence. Of this power series. Okay, radius of convergence. But if we have, as in case 1, so if the series only converges at x equals a, we say that the radius of convergence is 0. And if you think about the picture, this makes sense. It's a 0 width interval. And then what do we think we say for the second case? Well, if the series converges for all x element of R, we say the radius of convergence is infinity. Okay, so R equals 0, R equals infinity. Second definition. The interval containing all x such that the series converges is called the interval of convergence. So, interval of convergence. In case 1, the interval of convergence is just a single point. It's just a set containing A because you don't converge anywhere else. In case 2, the interval is all of R. So the entire real line, minus infinity to infinity. Now in case 3, it's a bit more complicated because we have a few scenarios. So in case 3, remember we have this R greater than 0. So the interval of convergence is either the open interval a minus r to a plus r, so you don't converge on either endpoint, or you converge on the left endpoint and not the right, or you converge on the right and not the left, or you might converge on both. Okay. So in this third case, we have 4 possible options for how the interval of convergence is going to look. Okay. So some people call the radius of convergence for short ROC. You might see this in questions, and the interval of convergence can be denoted by IOC. An example where we can determine the radius and interval of convergence. Well, we're going to keep coming back to the geometric series. Now we know this converges if and only if, so these are the only points where it converges, absolute value of x strictly less than 1, i.e. the radius of convergence is 1, because we converge for all x between -1 and +1. And the interval, just to express that concretely, the interval of convergence is the open interval from -1 to 1. And in line with what we said before, this is centered at 0, which makes sense because this power series we're looking at is a power series centered at 0. It's x to the n, which is the same as x minus 0 to the n. Okay, so I made the claim earlier that power series were easy to differentiate and integrate, so let's address this idea. So differentiation and integration of power series. We're going to encompass the ideas into a theorem, so differentiation and integration of power series. Theorem. If a power series sum and goes from 0 to infinity, Cn x minus a to the n, has radius of convergence r 1. The function defined by f of x equals this power series. So remember, each power series is going to describe a function. So the function defined by this power series, which is c0 plus c1 x minus a plus c2 x minus a squared, and so on, is differentiable and hence continuous, if you remember our Calc 1, and therefore continuous on the open interval a minus r to a plus r. And furthermore, we can give a formula for it. F prime x is equal to, well, n times cn x minus a to the n minus 1, from 0 to infinity. And this is exactly what we would get if we just naively differentiated each term. So the c0 would disappear, the c1 would just, the c1 x minus a would become c1, etc. So this is the formula for the derivative of the power series on the interval where it converges. Secondly, for absolute value of x minus a less than r, assuming you still have this radius of convergence r, the integral f of x dx is equal to some constant c plus c0 x minus a plus c1 x minus a squared over 2 plus dot 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 so on. Okay, which, if we summarize into the series notation, is this constant of integration c plus sum cn x minus a to the n plus 1 over n plus 1, where n goes from 0 to infinity. So NB, these two series for f prime and f of x integrated, the antiderivative, both have radius of convergence r. However, the interval of convergence may change, as you may lose the endpoints. So it may change at the endpoints. So for absolute value of x minus a equal to r. So again, you have to check these, even for the derivative and the antiderivative, you have to check these individually. So let's see some examples of this in action. Examples. Find power series representations of the following functions and state their radius of convergence. First example, g of x is 1 minus x squared under 1. Second example, h of x is equal to 1 over 1 plus x squared. Third example, j of x is ln of 1 plus x, so natural log 1 plus x. Fourth and final example, f of x equals arctan x. Okay, so at this point in the video, pause and see if you can solve these, and then I'm going to run through the solutions. Okay, so solution. 1. Consider p of x defined to be 1 over 1 minus x. Then the derivative of p of x is 1 over 1 minus x squared, which is equal to h of x. So, for absolute value of x less than 1, h of x equals the derivative of p of x, which is equal to the derivative of 1 over 1 minus x, which, and here's where we're using the assumption that the absolute value of x is less than 1, is equal to the derivative of this power series, which by the theorem is we just differentiate term by term, because that's what the theorem says, we can differentiate term by term. So theorem part 1. And we have found a power series representation for h. And here again is where we used absolute value of x less than 1. So r is equal to 1. Second example. In the exact same sort of vein, 1 over 1 plus x squared is equal to 1 over 1 plus x. The derivative is equal to, for absolute value of x less than 1, minus 1 to the n, x to the n, and it goes from 0 to infinity, take its derivative. And how do we take its derivative? We take its derivative term by term, using again theorem part 1. So minus 1 to the n times n, x to the n minus 1. And again, r is equal to 1. Okay, the third example is worked out in your notes, so see notes for that. Example 4, arctan x is equal to, well, it's the antiderivative, it's an antiderivative of 1 over 1 plus x squared, which is equal to integral. Remember, now this formula is going to be valid for absolute value of x less than 1. Integral of the sum minus 1 to the n, x to the 2n, from 0 to infinity. And what does the theorem say? It says we can integrate term by term. So we have our constant integration plus integrate term by term, minus x to the n, x to the 2n plus 1 over 2n plus 1. Now, how could you find that c? I'll leave that as an exercise. Try and find what the constant of integration has to be. Think what value of x could you plug in both sides to figure that out. So, remark, to find the interval of convergence, so we found the radius of convergence for each case, but to find the interval of convergence, we would need to check the endpoints. Remember, because it could be open, half open, or closed intervals. So what have we shown so far? We have the following power series representations of the below functions, the functions in this table, and we have the intervals on which the values of x make sense to plug into these power series. Where are these representations valid? Now, there's a question mark above some of the inequalities, and that is because we haven't checked the boundary cases. So we don't know exactly the interval of convergence. You would need to check it. For example, in the second from the bottom, the ln 1 plus x, you don't know if this will converge for x equals 1. So you need to check that individually. Okay. Similarly, for arctan, you don't know for either endpoints. Okay. And lastly, to finish up this lecture, let's look at the second use of power series that I mentioned, which is an application for estimations. Okay, so the easiest way to see this is, again, just an example. So, example, use the first 3 terms of the power series expansion or representation around 0 of 1 over 1 plus x to the 7 to estimate the following integral from 0 to 1/10 of 1 over 1 plus x to the 7 dx. Okay, so I'm just going to run straight into the solution. How do we do this? There are more examples in the notes that you can test yourself on. So let's just run through the solution. This integral, 1 over 1 plus x to the 7 dx, is equal to, remember this expansion is only valid for absolute value of x less than 1, but that's exactly in that interval contains the interval we're integrating over. So this is equal to sum minus 1 to the n x to the 7n dx, which now is roughly equal to, and we're just going to take the first 3 terms, because if we think about it, after this, so the first 3 terms are 1 minus x to the 7 plus x to the 14. The next term would be x to the 21, and for x close to 0, that's very small. So let's just do the integration. So we ignore the small terms. Okay. And if we plug in these values, if we plug in the limits, it's roughly 0.1. Okay, so this integral would have been very difficult to do by itself by just finding an antiderivative and evaluating, but now we have approximated it well enough by just using the first 3 terms in the power series representation around 0. So that's a lot simpler. It's one method for applying power series representations in a useful way.